Welcome to part 2 of chapter 10 on gaseous agent extinguishing systems. And today we're going to talk about the other kind of systems. We talked about CO2. Now we're going to talk about halon, inert agents, and aerosol products. So these are all different ways to extinguish a fire with our more technological type of situations where we have high dollar equipment that we want to protect. You know, I was thinking about an analogy on this. If you bought a high-end car like a Mercedes-Benz, or even more like a Bugatti or a Rolls-Royce, or whatever. Hey, how about a Maserati? Who wouldn't like to drive a Maserati? That would be fun. There's one that is in my neighborhood that I see every once in a while. He bought it in the most ugly color of yellowish green. I don't understand that. Why would you have the most fastest car on the block and then buy an ugly color? I don't know. But if you bought one of those kind of cars, wouldn't you want to get the best insurance you can? Are you going to go out and buy the budget insurance that if you get in a crash or if you have damage to your car, they're going to say, well, you have to go to the place where we tell you, and it's Joe's ding and crash fix budget guy down, in the bad part of town. No, you don't want that if you've got a high-end car. You're going to get the best insurance. You're going to pay more, but what you invested in your high-end car needs to be protected. So that's where these systems come into play. They're more expensive, they're complicated, they're expensive to build and install, but you're protecting something that's very valuable like computer banks. So let's talk about these systems. First of all, we have halogenated agents. Halogenated agents are a mixture of carbon with either fluorine, chlorine, bromine, iodine, any one of these kind of products. Now, there's different recipes out there, and these different companies have their own little version, and they give these numbers to them. The numbering system lists the number of atoms of each element in the agent. So it's kind of giving away their recipe a little bit, but there's Halon 1211, 1301, all of these different kinds of halon. Now, some of them have been deemed illegal because they found that they were doing damage to our ozone and that they're part of the problem with global warming. So halon agents do work. They're very effective, but some of them have been outlawed and are going away. There are still some halon and halogenated agents that are being used, and how they work is they actually, we've talked about the fire tetrahedron, and for the most part, for firefighters, we're thinking about the fire triangle. We want to take away the oxygen. We want to take away the fuel or take away the heat with water. But there is that fire tetrahedron, and this is one of the products that actually does that. It breaks down the chemical reaction that's going on between the three. So it breaks the link. And that's the basis of the fire tetrahedron, is that there's, in that triangle, there's links. You need the reaction going on. These products stop the reaction. So they're odorless, colorless, non-corrosive. They're non-conductive, non-toxic at low concentrations. Now, I'm going to say it once here. You're going to see this throughout this lecture. It constantly says, well, it's safe for humans in low concentrations. I'm just going to tell you, 10 years from now, they're probably going to tell us these products are cancer-causing if you breathe them, okay? So I don't go in these rooms until it's deemed 100% safe. Somebody has to go in with a monitor make sure that there's adequate oxygen, make sure that the product has dissipated, and then it's safe to go in. So I'm going to just say it right here. I don't believe them when they say it's safe. Anything that's not natural that goes into my lungs, it's bad for me. So that's my opinion. These are effective against Class B and C fires, a little bit against A's, but from the most part, we're thinking C with these. Electronics, electrical equipment, big, data banks and things like that, computer rooms. It can be used against flammable liquids, but remember, we've got foam, wet chem, dry chem, which are a little cheaper to make and develop and use than these kind of systems. So they're going to go with whatever works best. It's not suitable for reactive metals, materials that have oxygen in them, and oxidizers, and metal hydrides. Halogenated agents. There they say it. Human exposure is okay. Don't trust that. I don't trust it. I'm going to stay out of that. You're going to watch a video of a control tower where all of these men were in the room while the stuff activates, and they're lighting matches to see how it puts out the matches. It's a really interesting video. I would have said, you know what, I'll be outside for the test. That's just me. I've had enough health problems to where I don't trust all of that. If I don't have the proper protective equipment on, I'm going to be not in the room. They have about a 4 to 7% concentration. 10% they say is dangerous to humans or higher. Decomposition produces dangerous byproducts. So I'm staying out. I'm going to wear my SCBA or not be in there. These systems, again, if you bought a high-end product, I would say you want tailor-made things for it. Yes, they can be pre-engineered. I was thinking about this also. I have a small, nice little backyard. It's not a big deal. I've been thinking about getting one of those outdoor fire pits that are pre-made. Everything's set up. You either got to connect it to your gas line or use a propane tank. It'd be just fine for my yard. One of my best friends, though, he's a millionaire. He's got this backyard that his pool and all of the stuff he did in the backyard is more than $1 million. So he wanted to put in a fire pit. Well, no, he made a tailor-made, engineered just for his backyard, and it's a full-blown fireplace with a mantle and all of that kind of stuff, and a chimney, and it's all beautiful rock, and it kind of goes with the water fountain, the waterfall that goes into his pool, and all of that kind of stuff, and it's ornate. Well, you know, it makes sense. You got $1 million backyard, you put in the $150,000 fireplace. You got a little backyard with, a patio. You buy the thing at Lowe's for $100 and you put it in your backyard. Well, here we are. We're dealing with a very expensive equipment. We're going to engineer it and tailor make it for that situation. So there's lots of different components, and they've got to consider what's the product we're protecting. So do we need automatic detection or do we need manual controls? Do we need both? Most of the time, both. So all of this is going to be considered. A lot of them have to have an emergency release valve, and also they need to have abort switches. So these kind of systems, they don't want you in there unless you have to be in there when they go off. And so there's a pre-alarm that's going to go off. The pre-alarm gives you a chance to go and hit the manual abort switch. So if you look at the picture on your top left, the manual pull is right next to the switch that says, oops, I bumped this by accident. Or we turned it on, but before we actually needed it to activate, we took care of the problem. So you push the abort switch, and then this very expensive product doesn't come out. Okay, so again, it's going to be made just for every situation, and all of these things are considered. Nozzle placement is critical to a uniform delivery. So you got to they engineer it. One nozzle enough for the room, or do we need 4 in the different corners? So when the Halon comes out, it's stored in a cylinder like CO2 as a liquid, and it comes out as a vapor. When you see the vapor, it's very clear. It looks like a fog, and you'll see that in the different videos. Please watch those videos about activations. They're all really short. They're kind of interesting to watch. And you'll see that as the product comes out, it tracks moisture, and it looks like a big fog. Now, the fog will eventually dissipate and go away. That doesn't mean the gas is gone. The gas remains. So they do a hazard evaluation of what's the product, what's the size of the room, and they engineer it, and then they come up with, okay, we're going to use big cylinders, we're going to use small cylinders, 6 cylinders, that are small, or 2 cylinders that are big. They both do the same thing. Cost versus gain. What's the best situation? What size piping do we need? All of these things are engineering considerations. And then they come up with the final product. They present that to the inspector, who will approve or make recommendations for changes, and then they get to start building it. Okay, so they're specifically engineered per the NFPA standards. So 12A is for the different kinds of halons. NFPA 12B was for Halon 1211, and it's been discontinued. There are still some systems out there, but they're becoming obsolete. There's 2 ways to do it. And this is basically going to be true of all the systems except for one. There's local, like the CO2. We're going to spray it right on the equipment. Or there's total flooding, where we're going to have it. It's going to envelop the whole room. And we're going to flood it, like, from top to bottom with the gas. And it's going to fill it with Halon. When we're talking about the local flooding, where it's just on a location application system, we're going to have the nozzles are going to direct it to the hazard. It's appropriate when enclosing a hazard is not either possible or practical. Total flooding is preferred, but local application will be used when it's the only option. The nozzle placement, the type, all of that's critical to the product being sprayed on the equipment. It's a liquid stream agent here, and it's going to come out more liquidy than gassy. It will eventually turn to gas, but they need it to be directed, so it's going to come out like a stream. So it expands as a mixture of liquid droplets and vapor. Again, not going to use that unless the situation requires it. So then we have total flooding systems, and these protect enclosed hazards by filling the entire enclosure with Halon. And this is more common. The concentration levels are 4 to 15% by volume. Halon 1301 is the preferred product, and it's discharged in a uniform and rapid distribution. So here's a great illustration of a setup. And if you look at the gray kind of piping, that's the electrical, where the detection system detects something wrong, sends a message to the fire alarm control panel. It sends a message to the cylinders, and they open. So sometimes it's a little puncture thing, a little hammer punctures it. Sometimes it's a valve that releases. but it opens. And if you notice in this one, we have halon in the smaller containers to the left, CO2 in the bigger cylinders to the right. And the CO2 is being used to propel it. Now, we know CO2 is also an asphyxiant. It's going to take away the oxygen. So the CO2 is only going to help in putting out the fire, but it's mostly there to propel the halon through the piping, out the nozzles, into the room. It's pretty cool. And here's a close-up on the cylinders for the halon, and they're not under as much pressure, so they don't need as substantial of cylinders like the CO2. But the CO2 is going to press it out. Or sometimes they use nitrogen or something else. But something will be a propellant pushing out the agent of halon, and the halon puts out the fire. Now, there's another kind called clean agents, and they were developed to replace Halon 1301, and they're very effective on A, B, and C fires. So it's going to be used more often with, and now this is kind of the new thing, and is more common than the halon ones. It's for computer rooms, television broadcasting facilities, telecom facilities. Again, really expensive stuff. Shouldn't be used with reactive materials or things that are oxidizers, as we talked about with the other. We're going to see as we look at these other ones, it's kind of repetitive, but there are some differences. They say human exposure is okay. We already talked about that. I wouldn't do it. Clean agents fall into the category of inert gas. And there are basically two subcategories of that. Halogen-based agents, and they interrupt the fire's chain reaction. And then inert agents, they reduce the oxygen levels and asphyxiate the fire. The fire. Okay, so engineered self-contained systems, they use different components. It's going to be tailor-made, just like the other one. All equipment and components have to be listed and approved with FM, Factory Mutual and Underwriters Laboratories. Unlike the halogen, this system needs to be total flooding. So we're not going to use local application. We're choking the fire, so we're going to flood the whole room and take the oxygen away from the fire. So the system activates at the control head, valve opens, gas comes into the plumbing and flows to the nozzles, puts out the fire. Now, these have to have a delay. With the halogen or the halocarbons, it's 10 seconds delay. With the inert agents, they don't want you in there because there's no oxygen. So 60 seconds. Alarm goes off, 60-second delay before the inert agent comes in the room. And that's because everybody needs to get out, okay? Because you're going to die if you're in there. There's going to not be enough oxygen for you. There's auto detection and there's manual pulls, just like the other ones. It has to have that abort switch. And if there is an abort switch, it needs to be in the hazard area. And then warning signs with emergency information have to be posted in these rooms so that people know what to do if the alarm goes off. If you look at the left, the picture shows a device that it hammers and opens up the valve. And then on the right, you can see a typical nozzle for an inert agent. I didn't work on these a lot because I worked with schools and institutions. The hospitals sometimes had them, and so I did see them a little bit there. But I have seen them here and there, never oversaw the installation of one. But it is interesting. A lot of times, if it's a smaller telecom room, you'll just see one nozzle like that one right there, and that's adequate, given that it's a total flooding system. The nozzle placement is critical so that you get a uniform delivery, usually going to be in the middle of the room. And the nice thing is it's going to get to the difficult areas because it floods it. Just like you would flood a room with water from bottom to top, that's what it's doing. It's flooding the room with inert agent. Once the hazard evaluation is done, they're going to engineer it, and it's going to be just like what we talked about with the Halon agents. You know, the size and the number of cylinders is going to be based on the room, the pipe size based on the room, the type of nozzles based on the room. These kind are, the standard is NFPA 2001. I'm not going to hold you responsible to remember all of these NFPA standards in the test, but you just should know that they're out there, and that there are also other reference standards like NFPA 5000 and then some UL literature, UL 2127, yada, yada, yada. Okay? So, our last kind of product is Aerosol Fire Extinguishing Systems. Now, these are pretty specific and need to be total flooding in smaller spaces. It's a potassium-based compound. It undergoes internal combustion process and becomes an ultrafine spray. So this is a chemical reaction that's going to go on, and it comes out in an ultrafine spray. And like the Halon, it interrupts the fire chain and makes it so that the fire triangle can't keep going on, that chemical reaction. Once it's discharged, it remains in the environment long enough to prevent reignition, even if the stuff is still hot. It won't catch fire. Best for B and C. One of the places where you see them is like in jet engines, in military ships, and places like that, where in smaller enclosed spaces where it can flood, it needs to be closed. So it's NFPA 2010, and it's very specific, says it's not well suited for deep-seated fires, chemicals subject to rapid oxidation, reactive metals, chemicals that undergo autothermal decomposition. It's not going to work there. B's and C's, electrical equipment fire, a flammable liquids fire that doesn't have an oxidizer in it, it will work. And as you can see in this picture, there it is in a jet engine for a military plane or a military jet, and it really works well in that situation. They have their own special nozzles. Look at that cool looking nozzle. Kind of looks like a shower head, but not the ones with the low flow thing, you know, where you feel like you got to take a shower for twice as long because you're getting less water. But there's two basic kinds. There's condensed generators, where it's a self-contained canister, and it gets mixed with another product, and there's a chemical reaction, and then it gets shot out. And then there's dispersed generators. They already have the chemical agent in it, but it's pressurized by suspension in an inert gas or a halocarbon that helps push it out, and when activated, the pipes and nozzles distribute the aerosol. Well, those are our three kinds of systems. Well, they're all kind of, actually four, because we did talk about CO2 in the other lecture. They're all subject to approval, got to be approved by the authority having jurisdiction, and then it has to be inspected when it's being built, and periodically inspected, tested, and maintained, some by the owner's representative, like a facilities manager, or some by an approved state fire marshal company that's got the licensing and certifications to check these systems. The CO2 has to be weekly inspected on of the gauges on the low pressure systems, and once operational, they got to do visual inspections, make sure everything's in good condition, no leaks, and semi-annual inspection of the high pressure systems to make sure it's not leaking. Actuation tests need to be done on both low and high pressure systems. The hose systems have to be checked every 5 years. If they're unused for 12 years, then the tanks have to go a hydrostatic test. Halon is similar. Once it's installed and approved, it goes through that same process. Then they have to do functional testings and visual inspections on a regular basis. Monthly visual inspections to assess the hazard, any changes, any equipment damage, any leaks. You saw some pictures of systems where the tanks were outside. Well, they're subject to oxidation from the sun hitting it, and things can get damaged. They can get bumped by things, so by trucks or whatever. So we need to inspect them, make sure nothing is non-functional. We want to make sure if we need the system, it's going to function properly. So they have to have an annual actuation test and a pressure test every 5 years. Similar with the clean agent, operational annual visual inspection, semi-annual pressure loss checks, annual actuation tests. Hang on for this next slide. It's got a great picture. Annual inspection, pressure testing every 5 years for hose systems. And this is how they test a total flooding room. They have to put this canvas-looking cover on the door, and then they have this equipment that measures if any of the product is leaking out of the room. There's an allowable minimal amount of air leakage. Beyond that, it wasn't built properly, so they've got to make changes to the door or to the whole system. So the testing is very intricate. Last slide. The aerosol type, like other systems, requires the exception inspection, testing, periodic inspections and testing, 30-day visual inspection. Semi-annually, they got to weigh it, make sure the product is still in there. CO2 oftentimes is weighed to make sure the product is in there because it's liquid in the tank, remember, and then gas when it comes out. And almost all of these are that way. And then they have to do the enclosure test, make sure it's not leaking. And sometimes the manufacturer recommends stuff much more specific to their product than the state fire marshal says. So you need to follow those guidelines as well. That requires something us men don't like to do. It's called reading the instructions. So that's it on gas systems. I talked as fast as I could. Sorry, I tried to keep this shorter, but 27 minutes, 28 minutes, that's not too bad. I hope you guys are all healthy and safe. Have a great day. Thanks for watching this video.